In this session, let us try to discuss about starting of synchronous motors. Basically, starting of synchronous motors and kind of speed control of synchronous motors and kind of braking of synchronous motors and kind of harmonic torques. Okay, time harmonic torque, space harmonic torque in synchronous motors. Why we won't discuss all these four in synchronous motor is because of only one reason. Basically, if you have a motor, kind of induction motor or DC motor or synchronous motor, motors, the moment it's a motor, we should be able to control the speed or not. Yes. Okay, but in synchronous motor, if you take any standard book, any textbook, synchronous motor speed control will not be there in synchronous motor. Okay, if you think of for example, if my present speed of the synchronous motor is 1000 rpm, so 1000 rpm to 2000 rpm, if I want to vary the speed, increase the speed of the motor, that is speed control. If 1000 rpm has to be reduced to 0 rpm, that is braking, means we have to reduce the speed of the motor to 0. So speed control, braking. Whenever you have speed control, kind of speed control will be there in DC motor, speed control will be there in induction motor. So in both the motors, braking also will be there. But in synchronous motor, speed control is not possible by its own principle, okay, primitive principle. Okay, so because of that, braking of synchronous motor also will not be there. Okay, starting means directly we cannot start synchronous motor by its own. Why? Some reason will be there. Because of the same reason, speed control is not possible. Because of the same reason, braking is not possible. Okay, because of the same reason, means kind of harmonic torques will not be produced or will not be analyzed in synchronous machine. Okay, for these four, only one reason will be there. That reason we are going to discuss now. And one more thing is, in synchronous machines, we extended our discussion immediately after salient pole rotor. What we have extended, kind of if excitation is lost. Okay, if excitation is lost, what will happen? If power output requirement or torque output requirement is more than maximum torque developed by the motor, what will happen? We discussed. Okay, that extension, now we have to extend that particular discussion to induction machine also. Okay, so for these five, only one reason will be there. What are those five? Starting of synchronous motor and speed control of synchronous motor, braking of synchronous motor and harmonic torques in synchronous motor, and kind of extension of when this excitation is lost, what will happen? When output torque requirement, load torque requirement is more than maximum torque developed by the motor, what will happen? So for these five, only one reason, that is starting of synchronous motor. That's why basically we didn't discuss starting of synchronous motor in synchronous motor. Now we are comfortable with induction. Now we are going to extend that discussion. So synchronous motor, basically that's why multiple times I say. Okay, for example, if I say delta torque angle. Okay, so how we connected this particular delta torque angle to all rotating machines means we connected all three rotating machines. Kind of DC motors will be, DC machines will be there, and kind of in AC machines, synchronous machines will be there, induction machines will be there. These three can be connected from one point of view, that is torque angle point of view. Okay, we proved that torque angle delta will vary from 0 to 90 degrees in synchronous, and in induction 90 to 180. And in DC, we are going to prove that delta will be exactly equal to 90 in DC machines. So from delta point of view, all these three machines are connected to a single point or not? Yes. Okay. Now, don't think that we didn't discuss synchronous motor starting of synchronous motor in synchronous machines, but we are discussing here because connection is there. Means we are not supposed to divide, this is DC machine, this is induction, this is synchronous, this is faults, this is protection, this is stability. It's not like that. Everything should be connected to a single point. Okay, anyway, let us start our discussion. See, this is induction motor. Maybe let us kind of squirrel cage induction motor, and this is salient pole synchronous motor. Both are motors only. Okay, for single induction motor also we are going to supply with three phase. So see here, this is phase A, this is phase B, this is phase C. For these three, we are supposed to supply three-phase power. Okay, I am going to supply three-phase power from here. In synchronous motor also, we have to supply three-phase power, no, to the stator. So this is A, this is B, this is C, A here, B here, C here. This is three-phase power. 3 phase you are going to supply to the stator. Okay, and about damper bars, see here in salient rotor pole shoes, damper bars will be there. Already we discussed in synchronous motor or synchronous machines that if I think of this is pole, this is pole shoe, inside the pole shoe we can have damper bars like this. We can have damper bars. Okay, so these 3 damper bars will be short circuited in the front, short circuited the back also. Okay, kind of, see, let me see here. This is salient pole rotor. These 3 will be shorted at front side also, at the back end also. Shorted. Okay, kind of, see here. Under the pole shoe, damper bars are there. These 3 are shorted at the front and back. Kind of in this way. See here at the front end, these are short circuited. At the back end, these are short circuited. Okay, kind of, see, if I think of only means bars, okay, is kind of squirrel cage rotor or not? Yes. Okay, so squirrel cage rotor in the sense my rotor bars will be there like this. Okay, at the both end, here it will be short circuited, here also it will be short circuited. It's a squirrel cage rotor, kind of squirrel cage rotor. Now these 3 are short circuited at the front and back. Okay, see here, it is going to be short circuited at the front end, short circuited at the back end. These are going to be squirrel cage, kind of squirrel cage rotor. Okay, now let us come back here. Basically, why synchronous motors don't have self-starting? Self-starting in its principle, by synchronous machine principle, it cannot develop starting torque. Why it cannot develop starting torque? See here, for example, if I supply 3-phase power to the stator of both induction motor and synchronous motor, in both the machines we are supposed to supply 3-phase. So the moment I supply 3-phase power, what will happen? Immediately my stator poles will be formed. And one more thing is, salient rotor will be there only in synchronous machines. Why salient rotor is not possible to have in induction machine? This is very important interview question. This interview question also will be dealt here only in this. Okay, now poles will be formed, rotating magnetic field, automatically they will rotate in this direction. Okay, already we know that A dash, B dash, C dash, how many number of poles will be produced? 2. Okay, A dash 2 pole, A dash 4 pole, A dash 8 pole, in that way. Okay, so the moment my stator is developing rotating magnetic field, for example, I strongly holded the rotor not to rotate. In this sense, rotor is in standstill position. Okay, from basics of rotating machines. Okay, basic principles of rotating machines, what was the conclusion we got? In order to have steady torque, steady and continuous torque. Okay, in order to have steady continuous torque, 2 conclusions, okay, 2 points has to be met. What are those? Number of stator poles equal to number of rotor poles, first condition. And second condition is stator MMF and rotor MMF should be stationary in space, displaced by non-zero space displacement angle. Then only it is possible to have continuous electromagnetic torque. That's already we know. Right? Now, stator is rotating, stator MMF is rotating with maybe synchronous speed ns. Now, rotor, I holded the rotor not to rotate. Then, how much will be the frequency of stator? Maybe frequency of stator is f. Okay, so the moment frequency of stator is f, for example, you are sitting here. Okay, now already we know that for one revolution of ns poles, one pole pair, one frequency, one cycle will be induced. For example, one cycle you waited here, one cycle. Already we discussed this multiple times, but let me discuss again, because if I multiple times repeat, automatically it will go to the mind. Okay, see here, if I wait for one cycle of current in time, this particular poles will be rotated by one revolution. Now, if you are sitting here, as of now, poles are here. How much will be the induced voltage here? 0. After that, induced voltage is positive maximum. After that, induced voltage is 0. After that, induced voltage negative maximum. After that, induced voltage is going to be 0. So, if I wait for one cycle in time, already from rotating magnetic field, RMF basics, we know that means one cycle of current will give you one revolution of in space, one revolution of pole pair in space. If it is revolved by 1 revolution, here you are going to get 1 cycle of back induced voltage, back EMF. Okay, so if I supply 50 cycles per second, 50 cycles per second means if I supply 50 cycles per second current, this is going to be 50 revolutions per second, and induced voltage here is going to be 50 cycles per second. Getting my point, right? Now, if I strongly hold at the rotor not to rotate, okay, red is going to be like rotor, black is stator. If I strongly hold at the rotor not to rotate, how much will be the frequency of induced voltages in the rotor? It is not rotating. Rotor is not rotating. So revolutions are going to be same. Revolutions are going to be same. Then how much frequency of induced voltages will be there in the rotor? Same. Same as if it is 50 Hz. 50 cycles per second. Rotor induced voltages also will be 50 cycles per second. Okay. Now in the rotor, induced voltages are 50 cycles per second. Okay, so what about the currents? Currents also will be 50 cycles per second, because for the rotor both ends are short circuited. Okay, so some induced voltages are there in the rotor conductors, currents also will flow because it is short circuited by its own. So rotor currents will flow with 50 cycles per second. Okay, and already we know that these rotor conductors are space displaced or not. Yes. So when time displaced currents are flowing through space displaced winding, rotating magnetic field will come. For example, as of now, stator poles are here. Rotor is not rotating. Somehow I strongly hold the rotor not to rotate. Then here, rotor induced voltage is going to maximum. Here, rotor induced voltage is less than maximum. Here, rotor because of this particular pole, induced voltage in the rotor and this conductor. Rotor conductor is 0. So rotor induced voltage is maximum. Rotor induced voltage is 0. So time displaced voltage are induced or not? Yes. If you think of rotor leakage is neglected. Let us think of only resistance. If I think of only resistance, here current is going to be maximum. Here current is going to be 0. Here current is going to be less than maximum. So time displaced currents are flowing or not? Through space displaced winding or not? Then automatically rotating magnetic field will be developed. Rotating magnetic field, what is the equation of the rotating magnetic field? 120 F by P. Stator frequency is 50 Hz. Rotor strongly holded not to rotate. Then rotor frequency also will be 50 Hz. Now already we have seen that. In squirrel cage rotor, automatically rotor will produce same number of poles as of stator. Automatically it will produce. Already we have seen that. Okay. So rotor also is going to produce 2 poles. Rotor also is going to produce 2 poles. Now rotor is going to produce kind of 2 poles here, because rotor reactance is neglected. So delta is going to be 90 degrees already, you know. Okay. So this is going to be north pole of the rotor, south pole of the rotor. Frequency, stator frequency is 50 Hz, rotor frequency also 50 Hz. So rotor is standstill, not rotating. So with respect to rotor poles will rotate with same as ns. ns. Now n pole, s pole attraction will be there. S pole, n pole attraction will be there. N pole repulsion will be there. S pole repulsion will be there. Kind of torque development will be in this direction. Discussion over. Just let us extend this discussion. Okay. So when rotor is at standstill, I strongly hold at the rotor not to rotate. At that time, what is happening? Means number of poles of stator and rotor are same. 2 number of poles of the stator, 2 number of poles of the rotor. And even though rotor is at standstill, stator MMF with respect to stator is rotating with synchronous speed. Rotor poles with respect to rotor is also rotating with synchronous speed. So what is the angle between stator MMF and rotor MMF? Stator MMF and rotor MMF 90 degrees. And it is rotating with synchronous speed. It is also rotating with synchronous speed. So torque will be produced or not? Yes. Okay. So if I strongly hold at the rotor not to rotate, under that condition torque is there. And multiple times we have seen that maybe stator MMF is rotating with 3000 RPM. 2 poles, frequency is 50 Hz, 3000 RPM. If stator MMF is rotating with 3000 RPM, if rotor is rotating with 1500 RPM, what is the relative velocity? Is reduced. So what about the induced voltage frequency is going to be reduced? So if rotor is rotating with 1500 RPM, with respect to rotor MMF will rotate with 1500 RPM, because frequency is going to be reduced, synchronous speed is going to be reduced. Okay. For example, if rotor is rotating with 2700 RPM, 2700 rpm, and stator mmf with respect to stator is rotating with 3000 rpm. Rotor is rotating with 2700 rpm. About this we discussed a lot of times. Okay, so rotor is rotating with 2700 rpm. With respect to rotor mmf will rotate with 300 rpm, such that stator 3000 rpm, with respect to stator, rotor 2700 rpm, with respect to rotor mmf 300 rpm. Then also stator mmf and rotor mmf are standstill with respect to each other or not? Yes. Okay, so means angle will be there, displaced by non-zero displacement angle, means that angle is 90 degrees. So if rotor is strongly holded not to rotate, then also torque is produced. Torque is produced in this direction in order to rotate in this direction. Okay, and if I relieve it, rotor will be accelerated. Okay, when rotor is accelerated and when rotor is rotating at other than synchronous speed, because if rotor is rotating at synchronous speed, relative velocity between stator mmf and rotor will be 0, rotor induced voltage will be 0, rotor frequencies will be 0, so there will be nothing like RMF and all. Induction machine is synchronous machine. It should not rotate at synchronous. Any other than synchronous it can rotate. Okay, means though you know this, just focus, because it has to be compared with synchronous. Getting my point, right? Now anyway, independent of the rotor speed except synchronous speed, okay, independent of the rotor speed, stator mmf and rotor mmf are always stationary with respect to each other. That's why continuous electromagnetic torque is possible. Okay, that's why if I strongly hold at the rotor, starting torque is there. Now let us do the same analysis with salient rotor synchronous motor. Okay, or kind of without damper bars, in the sense these damper bars are not there, for example. Okay, then kind of if I think of maybe this is N pole, this is S pole, this is N pole, this is S pole. Okay, these are created because of the field windings. These are created because of the field windings. Okay, in synchronous motor we are going to supply DC current. Okay, so the moment you supply DC current, automatically DC poles are created at starting. Okay, now the moment you supply means three-phase supply to the stator. Three-phase supply to the stator, meaning that time displaced currents flowing through space displaced windings, one RMF will come. So stator RMF, same as induction motor, stator RMF will be produced here, N of stator, S of stator. These are rotating with synchronous speed ns. Okay, the moment you supply, basically these poles are virtual poles. They are not real poles. Virtually means it is giving the effect as if some two poles are rotating, is the concept of rotating magnetic field. Okay, now the moment you supply three-phase supply here, automatically poles will be formed. Poles will be rotating virtually with electrical time constant or mechanical time constant. Electrical time constant, because electrically currents are time displaced sinusoid. So means virtually these poles are formed, these poles are rotating with electrical time constant. About this also I have given previously introduction. Okay, now for example, I strongly hold at the rotor not to rotate. Then what will happen means my stator poles are fixed. Rotor poles are fixed. I'm really sorry. Rotor poles are fixed because at starting rotor is not allowed to start. Okay, about starting of synchronous motor let me deal. Okay, so poles are, this is N pole, this is N pole. Okay, so this is N pole. Now which is stationary? Now what about the stator poles? Stator poles are like created because of electrical time constant. The moment you give three-phase supply, okay, once you neglect initial magnetic interest and all, so stator poles are rotating, for example with 3000 rpm. Okay, if you supply 50 Hz supply to two poles, A dash, two pole, A dash, four pole, that way. Anyway, A dash, B dash, C dash, two poles it will create. Okay, the moment you supply to stator three-phase supply, immediately stator poles are rotating fast with 3000 rpm, electrical time constant. So for example, this is N pole, this is N pole which is stationary. Now for example, this is S pole, this is N pole, no, this is N pole. See here, this is N pole of the rotor, this is S pole created by the stator. created by the stator. For example, means my stator poles are rotating, right? This is S pole. Now the S pole as of now it is here. S pole as of now it is here. Now this is N pole. This is S pole. Now this is S pole in the sense it will try to, means it is rotating. Stator MMF is rotating, right? So this is N pole. This is S pole. Attraction will be in this direction. S pole, N pole, attraction will be in this direction, so it will be attracted in this direction. But these stator poles will not be like, will not stop for the rotor to have that magnetic coupling, okay? Because stator MMF rotate with 3000 rpm, rotor MMF is constant, stationary, because DC supply you are giving, DC supply you are giving, right? Now this is N pole, this is S pole, which is rotating. So the moment this is S pole, N pole, attraction will be there in this direction. Attraction will be there in this direction. It will be attracted in this direction. But by the time it will go here. Okay. This is N pole in the sense, this is S pole. No? Two pole structure. Let me compare. N pole, S pole. So this is S pole. So this is N pole. It is here. It is getting attracted in this direction. And by the time it move, it will go here. It will go here. This is S pole. This is also S pole. So repulsion will be there. By the time it will go here. Okay, so this is S pole, this is S pole, this is S pole. So repulsion will be there. Again, by the time it will come. Okay, simple logic. Simple logic. Okay, see here, this is N pole, this is S pole of the rotor. This is N pole, this is S pole of the rotor. This is S pole, this is S pole, this is N pole. So it is here. So it will be attracted in this direction. But my stator pole will not wait till rotor acquire that speed. Okay, because of huge moment of inertia, or I can say mechanical time constant is involved for the rotor, because it's mechanical, it has to be rotated. So this is N pole, this is S pole. So S pole is here. So attraction will be in this direction. After that, this is S pole, this is S pole. It will go here. So repulsion will be there in this direction. But after some time, S pole will come here. S pole, stator, S pole of the rotor, S pole of the stator, S pole of the rotor. Okay, so the moment it come here, S pole, repulsion will come here in this direction. And after that, again S pole will come here. N pole, S pole, attraction will be in this direction. Attraction will be in this direction. Okay, so the moment my stator poles are rotating very fast at 3000 rpm, 3000 rpm, and my rotor is associated with mechanical time constant. Okay, huge moment of inertia. So stator MMF rotate very fast. And rotor means will keep on vibrate with the mean position, but it cannot acquire the speed of 3000 rpm instantaneously. Okay, instantaneously 3000 rpm cannot be achieved. Okay, because instantaneously speed cannot be changed. Or in order to attain the speed of 3000 rpm for this, it needs time. Okay, for example, this is S pole, this is N pole. If it wait, this is S pole, this is N pole. If S pole is here only, if it wait, latched. Okay, S pole, N pole, and after that both can go in this direction. But this particular S pole is rotating very fast at 3000 rpm. So at one point it will be trying to rotate in this direction. At another point it will be trying to rotate in this direction. It will keep on vibrate, and it will be stabilized at only at 0 rpm. Okay, so what is the logic here? Stator poles are being rotated with electrical time constant. Rotor is associated with mechanical time constant. Okay, so for example, this is rotor, right? Rotor N pole, this is N pole, and these N and S are rotating very fast, My rotor cannot acquire the speed of 3000 rpm because of moment of inertia involved, so it will be there only. So if you think of rotor MMF, from N pole, rotor MMF is in this direction, stator MMF is rotating very fast. Okay, so stator MMF and rotor MMF, are they stationary with respect to each other? No, because stator MMF is rotating with synchronous speed in this direction. Of course, stator MMF is rotating in this direction with synchronous speed, and rotor MMF is stationary. So stator MMF is rotating, rotor MMF is stationary. So you don't get any continuous electromagnetic torque. Okay, because in order to have continuous electromagnetic torque, stator MMF and rotor MMF should be stationary with respect to each other, which is happening here at steady state conditions also, kind of stationary conditions also. Okay, if I strongly hold at the rotor not to rotate, then also stator MMF and rotor MMF are stationary with respect to each other. And if I release it, okay, if it is rotating with 3000, if rotor is rotating with 2000 rpm, then also stator MMF and rotor MMF are stationary with respect to each other. That's why torque can be produced. Okay, but here in synchronous motor you don't get that torque at all, because stator MMF and rotor MMF are not stationary with respect to each other, because rotor MMF is stationary at starting and stator MMF is rotating very fast, so you don't get torque. Somehow if rotor can attain the speed of synchronous speed, how we are going to discuss. Okay, if rotor can somehow attain the synchronous speed, then what will happen? If you think of this as S pole, if you think of this as N pole, somehow both are rotating at the synchronous speed. Okay, S pole, N pole, S pole, N pole, both are rotating at synchronous speed. Yes, it's fine. Now, for example, if you connect for this shaft, if you have the brake drum, for the brake drum, if you connect the load, then what will happen? Somebody is trying to stop my rotor. That is a load in a motor. Okay, then what will happen? This is S pole, this is N pole, maybe it will be delayed. Okay, it will be delayed delta. Then S pole will rotate with synchronous speed, N pole is also rotating with synchronous speed, then continuous torque is possible. Then continuous torque is possible because in this case stator MMF and rotor MMF are stationary with respect to each other, then torque production is possible. Okay, anyway, let me conclude here that my rotor MMF and stator MMF should be stationary with respect to each other, otherwise continuous electromagnetic torque is not possible. But this is happening in induction motor even at starting also. This is not happening in synchronous motor at starting, that's why starting torques are not possible. Okay, now let us think of speed control. For example, okay, stator MMF is rotating with 3000 rpm. Stator MMF is rotating with 3000 rpm. Rotor is rotating with 2700 rpm. 2700 rpm. Then okay, some torque is produced and rotor is stable, rotor is stable at the speed of 2700 rpm, rotor is rotating, all fine. Now, for example, you decided to increase the speed. In order to increase the speed, you increase the frequency to 100 Hz. From 50 Hz, if you increase the speed, frequency to 100 Hz, then what will happen? Frequency is doubled. So, means my electrical time constant, my stator poles are with electrical time constant because they are virtual poles, they are not real poles. Okay, so means, for example, before changing to 100 Hz, it was 50 Hz. At 50 Hz, let us consider, at 50 Hz, stator MMF is rotating with 3000 rpm, rotor is rotating with 2700 rpm, rotor MMF with respect to rotor is rotating with 300 rpm, such that it is rotating with 3000 and rotor MMF is also rotating with 3000, so stationary to each other, torque will be produced, that's over. Now, means rotor is rotating with 2700 rpm now. You change the frequency to 100 Hz. You double the frequency. Then stator MMF with electrical time constant means my speed will be doubled to 6000 rpm. 6000 rpm. 120 into 100 divided by number of poles are 2. 6000 rpm. Now, just before changing, at what speed rotor was rotating? 2700. Immediately after changing this to 100 Hz, rotor will be rotating at immediately at that instant, rotor will be rotating at 2700 rpm only, but stator MMF will be rotating at 6000 rpm. Okay, immediately after change of frequency electrically. So the moment you double the frequency, and then automatically my stator poles with respect to stator will be rotating with 6000 rpm, but rotor is rotating with 2700 rpm only. Then what is the relative velocity is more, induced voltages are more, currents are more, means the moment currents are more, rotor flux will be more, rotor is going to have strong poles, so torque will be developed. That torque, because of that torque, my rotor will be accelerated towards 6000 rpm. Okay, if stator MMF is, very simple logic, very simple. If stator MMF is rotating with 3000 rpm, if rotor is not rotating at all, torque is there or not? Yes. If rotor is rotating with 1500 rpm, torque will be there, relative velocity is there. If rotor is rotating with 2700 rpm, torque will be there. Okay, now if rotor is rotating with 2700 rpm and stator MMF is rotating with 6000 rpm, then again torques will be produced or not? Yes. Then rotor will be accelerated towards 6000 rpm because independent of the rotor speed, except synchronous speed, independent of the rotor speed, always in the rotor torque will be produced, because independent of the rotor speed, rotor MMF and stator MMF are stationary with respect to each other. Okay, so speed control is possible here. Now let us come back to synchronous. Okay, so in synchronous, for example, somehow you rotated the rotor. Okay, somehow you rotated the rotor to 3000 rpm. Okay, means at starting 50 Hz. So with respect to stator mmf is rotating with 3000 rpm. For example, rotor somehow you rotated to 3000 rpm. Somehow you rotated to 3000 rpm. Then what will happen? This is S pole. This is N pole. Both are rotating in this direction. Maybe if you connect a brake drum and if you apply load, it will lag. So this is S pole, this is N pole, both are rotating at synchronous speed. So always torque will be there or not, always attraction will be there. So it will continue. Now stator mmf with respect to stator is rotating with 3000 rpm. Rotor is rotating with 3000 rpm. So yeah, both are rotating at the 3000 rpm. Continuous electromagnetic torque will be there because stator mmf and rotor mmf are stationary with respect to each other. Okay, now in this case, for example, in the stator you double the frequency. Okay, for example, in the stator you double the frequency to 100 Hz. Then what will happen? My rotor is rotating with 3000 rpm. Okay, 3000 rotor is rotating with 3000 rpm. When you supply to stator 50 Hz, then both are rotating at 3000. Now all of a sudden you increase the frequency of stator to 100 Hz. Then my stator mmf will be rotating with 6000 rpm, but rotor will be rotating with 3000 rpm. 3000 rpm. What is the relative velocity between stator mmf and rotor mmf? Is 3000 rpm. Again, will you get any accelerating torque? No. In order to have continuous electromagnetic torque, stator mmf and rotor mmf should be stationary. But here, rotor poles are stationary with respect to rotor. Why? You are supplying DC. Okay, so it is rotating with 3000. It is also rotating with stator. It is also rotating with 3000. Continuous torque will be there. But the moment you double the frequency, means it almost instantaneously, in the sense with electrical time constant, these poles will be rotating with 6000 rpm. 6000 rpm, and this is rotating with 3000. Will you get any torque? No. Okay, because when relative velocity between stator mmf and rotor is high, in synchronous motor you don't get any torque. So speed control in synchronous motor, do we need to discuss? No. No, because at starting what's happening? Stator mmf is rotating with 3000, rotor is stationary, you don't get the torque. Maybe in the next case, rotor is rotating with 3000, stator mmf is rotating with 6000. Will you get the torque? No. Okay, conclusion is very simple. What is that? When relative velocity between stator mmf and rotor is high, okay, you don't get the torque. But when relative velocity between stator mmf and rotor is 0, then torque will be produced. Okay, so speed control, it is not required to analyze in, say, synchronous. But if you think of in induction, speed control will be there. Now the moment it's speed control from 3000 rpm to 6000 rpm is possible. From 3000 rpm to 0 rpm is also possible. That is braking. Okay, so kind of, for example, we call this as a dynamic braking. In braking we will see, for example, rotor, stator mmf 50 Hz if you supply, with respect to stator mmf is rotating with 3000 rpm, rotor is rotating with 2700 rpm. Then stator mmf and rotor mmf will become stationary with respect to each other, independent of relative velocity between stator mmf and rotor. So torque will be produced, rotor will be continuing its rotation. Okay, for example, in the stator, if I supply DC supply, means it is rotating at 2700 rpm. If I stop supplying AC, if I supply DC, stator mmf will not rotate. Rather than that, stator poles are going to be stationary. Then the moment stator poles are stationary, the moment it is rotating with 2700 rpm. About dynamic braking we will see anyway later. Okay, ultimately if stator mmf is stationary, if rotor is rotating with 2700 rpm, so because of relative velocity, induced voltages will be there, currents will be there, rotor flux will come, interaction of stator flux and rotor flux will create torque. So that torque will try to stop the rotor. Now if you think of here, okay, at starting both are rotating with synchronous speed, 3000 rpm, happy. Okay, torque is produced, it is happy life. Now, means stably it is operating. Now, this particular 3000 rpm is not 3000 now, it became stationary. N pole or S pole is stationary. But this is rotating with 3000 rpm. This became stationary because you supplied DC supply to the stator. Then, means my stator mmf is stationary with respect to stator. By rotor is rotating with 3000 rpm. Will you get any torque here? No. Okay, so braking is also not possible. Braking is also not possible. Now, let us think of about the harmonics. We will have a detailed, deep discussion. But anyway, let me give you overall view. Okay, for example, see here, in this case, if it is rotating with 3000 rpm, if it is rotating with 2700 rpm, or if it is not rotating, forget about all. For example, stator MMF is rotating with 3000 rpm with respect to stator. Rotor is not rotating. I strongly hold it the rotor not rotating. Then torque will be there or not? Yes. Now, stator fundamentally is rotating with 3000. Okay, stator fifth harmonic component may rotate at 5 into 3000 or 3000 by 5. That depends upon the time and space. Okay, many guys do many mistakes here, but anyway, gradually you will come to know. Okay, see here, if because of harmonic component, this is fundamentally is rotating with 3000 rpm, maybe fifth harmonic may rotate at 3000 by 5 or 3000 into 5, 3000 into 5. But in both cases, if stator is stationary, okay, fundamentally is rotating with 3000, fundamentally is rotating with 3000, rotor is not rotating, torques will be there or not? Yes. Forget about fundamental, fifth harmonic space, about space and time I'll tell you. Okay, so fifth harmonic space, if it is rotating with 3000 by 5, okay, 3000 by 5, 3000 by 5, rotation and all we will see later. Anyway, if it is rotating with 3000 by 5, again that particular torque also will be there here on the rotor or not? Yes. Seventh harmonic may rotate 3000 by 7 or 7 into 3000, that depends. Okay, so if my rotor is stationary, fundamentally is rotating with 3000, fifth harmonic is rotating by 3000 by 5, let us consider space. Seventh harmonic is rotating by 3000 by 7, 11th harmonic is rotating by 3000 by 11, 13th harmonic is rotating by 3000 by 13. All these harmonic torques will be there in the rotor or not? Yes, because independent of rotor speed, torques will be produced in rotor, in induction. Okay, for example, let us apply the same. Okay, means about harmonics detailed discussion will happen, trust me. Okay, anyway, coming to here, okay, fundamental, let us consider fundamental. For example, rotor is also rotating at synchronous speed in stable conditions. So this is fundamental which is rotating with 3000, and rotor pole also rotating with 3000. This is S pole, this is N pole, this is rotating with 3000, this is also rotating with 3000, so both became stationary with respect to each other. Okay, so this is rotating with 3000, this is rotating with 3000, this is S pole, this is N pole. Torque will be there, torque will be produced in this direction because of attraction. S pole, N pole, attraction will be there, so because of attraction continuously it will be fundamental. Okay, so if I think of fundamental 3000, pole, rotor pole, so this is rotating with 3000, this is also rotating with 3000, torque will be there. For example, if I think of fifth harmonic space, this is fundamental 3000, fifth harmonic space, focus, fifth harmonic space. Okay, so fifth harmonic space will rotate with 3000 by 5. Okay, so fundamental torque is produced, now fifth harmonic is rotating in this direction with 3000 by 5. It is rotating with 3000, rotor is rotating with 3000, but stator MMF is rotating with 3000 by 5 or 5 into 3000, that depends upon space or time. We'll discuss about space or time later, harmonics and all. Okay, will you develop any torque? No, because see here, fundamental 3000, my rotor pole 3000, S pole, N pole, torque will be there. So both are rotating in this direction. Fundamental torque will be there. For example, fifth harmonic is rotating in this direction with 5 into 3000 or 3000 by 5. Okay, let us consider 5 into 3000. So if it is rotating with 5 into 3000, it is rotating with 3000. 5 into 3000, 3000. What is the relative velocity is high? Will you develop any torque in the rotor? No. So that's why harmonic torques need not be produced. Getting my point, right? Harmonic torques will not be produced. Why? Because with respect to harmonics, each can be space or time. Okay, relative velocity with respect to harmonic RMF and rotor will be high. So because of that, harmonic torques will not be produced. So what is the conclusion here? In induction motor, all harmonic torques will come, because if fundamentally is rotating with 3000, fundamental torque will be produced. If fifth harmonic is rotating with 3 into 5, 15,000. If fundamental is rotating with 3000, fundamental torque will come. If fifth harmonic is rotating with 15,000, torque will come. Okay, so fundamental torque will come, fifth harmonic torque will come, seventh harmonic torque will come, 11th harmonic torque will come, 13th harmonic torque will come. But if you think of here, harmonic torques will not be there. Harmonic torques will not be there. Why? Because the moment you think of harmonic, okay, kind of fundamentally is rotating in this direction with 3000, rotor is also rotating with 3000, then torque will be there. If fifth harmonic is rotating with 15,000 and rotor is rotating with 3000, what is the relative velocity between MMF, stator MMF, maybe kind of harmonic MMF, and rotor is high? Whenever this is high, torque will not be produced, means at mean position it will keep on vibrate. Okay, so what is the conclusion here? In its primitive principle, in its own principle of synchronous machine, without any damper bars, okay, because if you have damper bars, automatically this will come here. Okay, anyway, without any damper bars, in synchronous machine, in synchronous motor, is it possible to have speed control? No. Okay, is it possible to have braking? No. Is it possible to have starting torques? No. Will there be any harmonic torques? No. Harmonic torques? No. Okay, so all these things is not possible in synchronous machine. Why? Because of only one reason. What is that? When stator MMF, relative velocity between stator MMF and rotor is high, means not zero. Okay, when stator MMF and rotor MMF will be stationary with respect to rotor only. When relative velocity between stator MMF and rotor is high, continuous electromagnetic torque is not possible. But in induction, independent of relative velocity between stator MMF and rotor, except synchronous speed, independent of relative velocity between stator MMF and rotor, torques will be produced. That's why all these things are possible. Okay, so whenever you have speed control in any motor, automatically braking will be there. Whenever you have speed control, automatically starters will be there. In DC motor, starter will be there. In induction motor, starter will be there. In DC motor, speed control will be there. In induction motor, speed control will be there. In DC motor, braking will be there. In induction motor, braking will be there. Of course, in DC, it is just DC. Harmonics need not be analyzed, because if you love sinusoid, if you see any non-sinusoid, if you love sinusoid, if you see any non-sinusoid, then that non-sinusoid I will convert Fourier. Okay, Fourier will convert into so many sinusoids. One I'll take as fundamental, remaining I'll call it as harmonics. But in DC motors, like it is DC, that's it. Okay, but if you think of AC motors, okay, whenever you expect sinusoid, if anything is non-sinusoid, then concept of harmonics come. Okay, anyway, harmonic torques will be there only in induction, not in DC. Okay, now anyway, about starting we have to discuss immediately. In the next part I'm going to discuss about the means how it has to be started. Okay, conclusion is very simple. Okay, and about one more thing is like if excitation is lost, if what do you say, prime power input is more than maximum torque developed in case of generator, or when load output torque requirement is more than maximum developed torque in synchronous motor, what will happen and all we are going to discuss in the next session. Okay.